Hello and welcome to Chapter 2 of your online lectures. Chapter 1 was kind of long, and I understand that. Hopefully Chapter 2 won't be as long as we'll kind of move through it. So we're going to talk about chemicals, a little bit of chemistry, give you a little background. And here are the big ideas. So elements, atoms, compounds will be part 1. Part 2 will be the chemical bonds. And part 3, water's life. Part 3 is going to be all about water, and we'll see how important that is. So essentially, chemicals are what make up the physical environment. Once you break everything down, you have a chemical or an element that it is made up of. And everything we have when we're dealing with biology is that life is tied to water. The chemical reactions in our body, they all take water. Living organisms require some sort of water in some way. And life first evolved in water. We'll look a little bit like that. We'll look at that a little bit. So, elements, atoms, compounds. Living organisms all are composed of matter. If you weren't composed of matter, you wouldn't have any weight, you wouldn't have mass. So matter has weight, has mass, and in this case it says occupies space and has mass. So if you didn't occupy space, if you didn't have any weight, you would not be composed of matter. But there'd be no way to measure you. So matter is all built up of these elements. Each element, once you break things down into smaller and smaller and smaller pieces, you get to a point where you can no longer break something up and still have it be whatever it is that we're calling that. So if we get to carbon, per se, we can break it down to one carbon atom. Once we break that down more, it is no longer carbon. So that's what we're talking about when we're dealing with elements. And there's 92 elements, and very few exist in a pure state. Here are some common elements in the human body. So we have a lot of oxygen and carbon and hydrogen, nitrogen. So these are all different things that make up our bodies. And if you look up, 96% of our body is oxygen, carbon, hydrogen, and nitrogen. Just those 4 elements themselves. So it's really interesting. The different combinations of those are what make us up. Now compound, that's when you add 2 different elements together. So hydrogen and oxygen, you add them together, it now becomes water. That is a compound. Sodium chloride, so you take sodium, you take chloride, you put them together, it's a compound that makes salt. So here we are, sodium. And interestingly enough, sodium and chlorine are 2 very dangerous elements, very dangerous to the human body. But then when you put them together and create salt, all of a sudden we can use them. It's a usable compound. There's a certain number, about 25 of these elements that are essential to life. And of course, you would think the 4 elements that make us up, those would be the most essential. And that is, of course, correct: oxygen, carbon, hydrogen, nitrogen. But then there are trace elements, and they're essential, but they're only needed in minute quantities. So you think of an iron deficiency. So iron is an element that's very, very important in the body, but we don't need a ton of it. We don't need to eat an iron skillet every morning. In fact, just very, very trace amounts or small amounts of it are enough to help us. So some of these trace elements are required to prevent disease. This lady here has a goiter. It's a thyroid disease. And very often you'll see them put iron in salt. You go buy table salt at the grocery store, and you'll see some iron in it, and that helps prevent goiters. So you see goiters in third world countries where they're not getting enough iron. Another trace element is fluoride, and fluoride is actually very dangerous element, but in trace amounts it's very helpful to us. And so they put very trace amounts in toothpaste and in water supply. Incidentally, every water supply has arsenic in it, and arsenic is very dangerous, but in very, very minute quantities it's not dangerous. So it's very important that we understand the quantity of certain elements can be very important. Not enough and you can have damage, too much you can have damage, but certain dangerous chemicals and trace amounts are not dangerous. So, like I talked about before, sometimes add chemicals to food to help preserve it, make it more nutritious, make it look better. Your Doritos potato chips have MHC in it. Essentially what that compound does is when you eat it, it makes your body think you're eating meat. So your body says, this is good for me, and you want to eat more even though it's eating corn. So sometimes it's a good thing, sometimes it's a bad thing. But if you look at your food, there's a nutritional facts and label, and we're going to get into a little bit of this to help you understand things a little better. So when you go to the grocery store, you can be a little bit more informed. So the elements, we're talking about breaking them down, and when you break them down to a certain amount, they become an atom. One atom, it's the smallest unit of matter. It still has the same properties. So break everything down to one atom of carbon, break everything down to one atom of oxygen, so on and so forth. But once you break it down past that, it is no longer carbon or no longer oxygen. And when we look at these atoms, atoms are made up of essentially, we'll call them 3 subatomic particles. And if we want to get into nitty gritty, there's more, but for this class we're just going to stick with these 3 and keep it simple. So there's protons. They're positively charged. Neutrons. They're electrically neutral, and those are in the nucleus of the atom. Okay, they're in the very center. And then electrons are negatively charged. And electrons essentially have what they call a negligible mass, meaning their mass is something times 10 to the negative 26 or something, some just very, very minute quantity. And protons and neutrons don't weigh much themselves, but they weigh a heck of a lot more than electrons. And let's get to, when we get to a diagram, we'll talk a little bit more about that. So the neutrons, protons are in the nucleus, electrons orbit the nucleus, and interestingly enough, those electrons are traveling at the speed of light, and they are everywhere and nowhere at the same time. It's really kind of cool when you get to the physics of it. So the negative charge of those electrons, positive charge, they keep things together. And when you think about it, when you push down on your desk or when you push on the key of your keyboard to log in and view this video, it can be argued that you never actually really touched that key. That simply the electrons that repel each other got to the point where one moved and the other didn't. So you can. It's a fun argument to think about, but think of it that way, that we never actually really touch anything. The protons and neutrons never actually really touch. It's the electrons that are repelling that cause us to feel that we are touching things. So you have your nucleus. Here's your protons and your neutrons, and then the electrons. So protons, neutrons, here are your electrons. So well, we got a problem here. This is a little model. It's fine. It's simple, but if we really looked at this, if we think about it this way, helium, if the nucleus here, this nucleus, was the size of a pea, okay? Pea is about yay big, Skittle size. If that's, which they're much smaller than that, but if they were that size, this is just for comparison, the electrons would be orbiting about in a distance roughly the size of a baseball stadium. So if you put a pea in the middle of a large baseball stadium, the electrons would be kind of running around the outside of that stadium. That's how much space there really is in between the nucleus and the electrons. That's why people say we're mostly made up of space, and that is correct. There's just a lot of space between those protons, neutrons, and electrons. So this is important. This is always on test, and people always miss this. The number of protons is the atomic number. So if I give you an element with 12 protons as the atomic number, we can change the number. It should have 12 neutrons, and it'll have to balance the positive, negative charge. But if we remove a neutron and make it 11, it's still that same element. But if we remove a proton, it is a completely different element. So you can remove electrons, or you can add electrons, you can remove neutrons, you can add neutrons, and it'll stay the same element. But the moment you change the number of protons, that element changes. So an atom's mass number is the sum of the number of protons and neutrons in the nucleus. In this case here, the mass would be 24. The atomic number would be 12, but the atomic mass, or the mass number, would be 24. And so the atomic mass is approximately equal to its mass number because of the protons and neutrons. But just remember mass and number, and keep those straight. So here's carbon. Has 6 protons, 6 neutrons. The mass number is 12. It has 6 electrons, but remember we mentioned that the weight of the electrons is negligible. Okay? And so you can have all atoms of an element have the same atomic number, but they can differ in mass number. Right? And so you get isotopes. And isotopes, they have the same number of protons, but different numbers of neutrons. And remember, we can adjust the number of neutrons and still have it be the same element. We just can't adjust the number of protons. If we do that, it changes an element. So when you have different isotopes, it's going to behave differently. How and what I mean by behave is any sort of reaction that occurs is going to be different if it has a different number of neutrons, because it'll either it can have a stronger positive, or if you mess with electrons, negative, depending on what's going on. But in a radioactive isotopes, the nucleus will decay spontaneously, and that'll give off particles and energy. And we can use radioactive isotopes to date things. You've heard of carbon dating probably, where we look at carbon and look at the number of carbon-14 isotopes because they will decay spontaneously. And we know there's a certain percentage of carbon-14 per number of carbons, and how that and the timing of that. And so we can date something fairly precisely using that. If we go to different elements, we can date in the millions of years, and I believe we can date in the billions of years with some elements because we know how they decay. So, isotopes of carbon, so proton 6, neutron 6, electron 6, the mass number is 12. But if you add a neutron, you're going to get a mass number of 13. If you add 2 neutrons, you get a mass number of 14. Okay? And most carbon molecules are carbon-12. Carbon-14 is a very, very limited percentage of those. And we know it's a consistent percentage. So our cells, interestingly enough, are unable to distinguish between isotopes. And so we use this radioactivity, we use this in medical procedures because our body is unable to distinguish between that. And so we have PET scans, or we use radioactive tracers for diagnosis, and so we can look at heart disorders and cancers and use brain research by putting these chemicals in and kind of watching where they flow and how they flow, because they give off a different image than the normal chemicals. And here's a picture of that PET scan. And so on the left is a healthy person's brain, and on the right is an Alzheimer's patient's brain, and you can see them losing memory ability. But when we're dealing with radioactive materials, if we're exposed to them, they can break the chemical bonds that DNA uses, and so they can cause mutations, they can cause death, and all sorts of different things. When we dropped bombs on Hiroshima and Nagasaki, we initially killed a certain amount of people, but then we killed far more in later years, and for a generation or two, lots of babies were being born with defects and things like that because of the exposure to radioactive elements. And unfortunately, initially our government denied this, and then we later accepted responsibility for this. So that is part one. There's going to be some questions. Maybe they already pop up, and when I add questions, it just depends on where I click. That's part one. Do the questions, and then we will move on to part two.